Morning, Suvani.
Morning.
Hey, Timmy. That's all right. Yeah, actually, I'm gonna focus. All right. So again, today, guys, it's going to be like I'm just going to try to hammer through content for us. Okay. I might have a few demonstrations to show us, but the goal is to get you guys content, and then tomorrow, Thursday, Friday, as I'm out, like there's things that you guys can work through. So not a super fun day, but you know, I wanted to do a lab, but getting the content I think is more valuable, and then maybe next week at the beginning of the week we can kind of look at the lab and see what that looks like. Okay, so for those at home, can everybody see the board okay? I guess I can't really. Yeah, okay. I'm going to live stream this on YouTube as well, and then I'll edit it down, and that way it'll kind of be, we'll kind of have it in the archive as well, in terms of what the notes look like for today, right? I don't know what the legality of all that stuff is, but we'll figure it out after the fact, okay? So what we're looking at today is the idea of thermodynamics. Okay, and really we're going to try to understand how the physics behind something like, essentially, you know, if we have a setup like this, where we have basically air particles within this cylinder, right? And I have a plunger right here, which I can then do work, essentially, to compress the air, okay? And we're going to try to understand like what's happening to the air inside of here, or you know, what we'll do in the lab when we finally get to the lab is, I'll just cut myself off, is essentially what we're going to do is have this setup here, right, where we have you know, a syringe of air, essentially, with this is an air pressure, a pressure gauge right here. And what we would expect is when I put this mass on top of it, what's going to happen?
It's going to go down.
It's going to go down, right? So my volume is going to decrease, and my pressure is going to increase, right? And as I add more masses on top of this, we would expect that volume to continue to decrease. Yes? And so this is a way that we can increase the pressure of my system. And what's happening is I am doing work on the system. Yes? Like these weights are compressing this, they're applying a force downwards, and they're moving this downwards, right? So they are doing work, okay? And so what we're going to look at is understanding what's the energy happening of the particles inside of here, right? And understand how we can relate that to the work that is occurring, as well as the temperature that would be occurring in there as well. Does that make sense? Why don't you guys up here kind of come up here and we'll just do this demonstration kind of real quick. You guys can come up a little bit closer so you can see. Okay, people at home, you guys should be able to see. So this is called a fire syringe, right? And this syringe is, you know, like I said, it's a plunger here. There's a little tiny piece of cotton. Can you guys at home see that little tiny piece of cotton that's inside of here? But it's heavily insulated, and it's heavily insulated to not allow heat to go in, or really, it's not allowing it to go out, okay? because what we're meant to do with this is we're just going to hit this really hard, compress the air very quickly, right? So our volume is going to decrease very quickly. Our pressure is going to increase very quickly. And what we should see is we should see the ability to actually light this little piece of cotton on fire, because we're going to increase the internal energy of the air very quickly, right? And so from that, it should reach the combustion level that the cotton requires, and it should light it on fire. Just very quickly. It'll go out very quickly as well. But let's see. If it doesn't work with this one, we might have to just get a different piece of cotton, but we'll see. All right.
Ooh.
Okay, people at home, did we see that?
Yep.
Cool, yeah. So what we're going to look at is the physics behind, like, why does that occur, right? This is applicable to combustion engines, right? If we're looking at a car or like a lawnmower, like, why do engines work the way that they do? I'll actually have a video for you guys to watch. It's a really good one by Smarter Every Day over the next few days that looks at a combustion engine and looks at, what we're talking about here and how it actually is applied in a combustion engine. Cool?
I actually watched that yesterday.
Did you? Where they have like the clear acrylic top?
I don't know if it was the same one, but it showed how a combustion engine works.
Okay, yeah, there's one that he does one where like they have a combustion engine and they have a clear top, so you can actually see the combustion happening inside the engine, which is really cool. So let's talk about like the thermodynamics that's happening with that, okay? And then like over the next few days, you guys will be trying to apply that idea to different circumstances. Is that cool? Yeah. Okay. All right. All right, so how we're going to look at this is we're going to apply these two equations. One is the change in internal energy is going to equal the heat plus the work done in a system. Okay, so this is a change in energy. This is the heat added or lost, and this is work done. Okay? These are the main two equations that we're going to use. The work then, and Brian, this is kind of what you were asking at the end of the day yesterday. Work, what we're going to do is we know, we already talked about yesterday that in a pressure, like let's think about this. Let's think about this fire syringe, yes? Think about this fire syringe. What happened, right? We started in this scenario. This is our volume initial, yes? And we had very low pressure. This is my pressure initial, right? And then what changed?
The volume decreased.
The volume decreased, right? So the volume went to a very small volume. So this is my volume final, yes? This is my fire syringe. And what happened then to my pressure? It increased, right? My pressure went up somewhere here. So we have this, here is my initial situation. And here we have my final situation, okay? And this is my pressure final, right? And so what we are going to look at is, the process to get there. This might not be exactly what the graph would look like, okay? But we talked about underneath this graph, thanks, Arsene. Right, what is that there? That is the work. No distraction. Okay? That's the work that just took place. Okay? And so what we're going to measure this work as is negative pressure times the change in volume. Okay, that's how we're going to measure. And these two equations are on our reference sheet. Okay? These two equations are on our reference sheet, so that's how we're going to really, these are the bulk of what we try to do. Okay? So here's what we're going to look at. For the fire syringe, guys, did my internal energy increase? So did my internal energy, yes? Did it increase, decrease, or stay the same? I know
Increase.
It should stay the same.
it's going to increase in this case because what happened to the temperature in here?
Yeah, it increased.
It increased.
But the volume decreased.
Right. But the internal energy, right? This is basically measuring temperature. Okay? The change in energy is basically measuring the temperature. Because what does temperature measure? Yeah, temperature measures the kinetic energy of the particles. Yes? And so if my temperature goes up, my internal energy must go up. Right? You guys okay with that? So in this case, what happened was in the fire syringe, it's insulated. Okay? It's well insulated. It's a very thick acrylic tube, right? Which does that allow heat to be added or lost very quickly? No. So there's not a lot of heat transfer, yes? So this Q is basically 0, yes? The Q is 0. And then what did we do was we did a volume. Now look at this, guys. We did a volume from a big volume to a small volume, yes? So what is for my fire syringe, what is my change in volume? Is it a positive or a negative? It's a negative, yes? Change in volume, this is volume final minus volume initial, yes? For my fire syringe, we went small minus big, yes? Which for my fire syringe is a negative change in volume, yes? Okay? So look at this. Obviously, my pressure is a certain value. We don't know what that was. But look, negative P times negative delta V, what does that make this W? Positive. Okay? And what we know from my fire syringe, so here's the thing. For the fire syringe, right, our change in energy equals Q plus W, yes? Equals 0 plus W. So what does our change in energy equal? It equals W, yes? What does that tell me is going to happen to the internal energy, to the kinetic energy, to the temperature? The temperature is going to go up. Yes? We okay with that, guys? Okay. And so let's look at a few circumstances with this. But that's kind of how these two main things are related to one another. Okay. The work. So when I go from here to here, right? Let's put it all out in writing, and it'll make sense. Let's put it all out in writing. It'll make sense. Okay. Here's what we want. Let's think about this scenario. Let's say we have our particles here, right? We have particles here. Let's just go through a few examples of this. We have particles filled with gas, okay? It has a fixed pressure. It has a fixed volume, yes? Everything is fixed, okay? We take it and we submerge it into an ice bath, yes? We take it and submerge it in an ice bath, okay? What's going to happen? Let's just talk about it. What's going to happen?
I mean, the change in energy will be.
Right? In terms of Q and W, what's going to happen?
There's going to be heat loss.
Good. Yeah, so heat is lost to the back. You guys agree with that? Heat is lost to the back. So that's going to make my Q a negative Q. Yes? Deal. You okay? You okay over there?
Yeah, I'm good.
Is that you making all that noise?
Probably.
All right. Heat is lost to the back. Yes? That's a negative Q. If, in terms of work, my volume is fixed, right? If my volume is fixed, can there be any work?
It's just.
Right? If this value doesn't change, is there any work?
Yeah.
If this value doesn't change, if this value doesn't change, the change in volume is
Zero.
Yes? So then my work is 0. So in terms of work, that's 0 because volume is fixed. Yes? So what does guys, this makes sense, right? But what happens to my internal energy? It goes down. My internal energy goes down because temperature goes down. Yes? Okay, let's draw what would a pressure versus volume graph look like for that. What would a pressure versus volume graph look like for that? Volume's constant, yes? So let's just, right here, let's just do this. This is my initial position. Right? We have some pressure initial. We have some volume initial, yes? You said the volume stays constant, yes? Okay. What do we think happens to the pressure?
Is it just going to go down?
It's going to go down.
So it's just a point.
Pressure final. So my graph did this. My graph just did that. You okay with this? Brian? Sorry, it's hard to see.
Is there a relationship between the pressure and the temperature?
Absolutely. Due to pressure PV equals nRT. Yes? Okay? Ideal gas law. Here's the idea. Volume stays constant. N is my number of moles, right? If that stays constant, I don't let any air in or out. R is a constant value, yes? So as temperature drops, what happens to my pressure? It drops as well, right? As temperature drops, my pressure drops as well, okay? This is something that's called isobaric. No, isochoric, I think, actually. Yeah, sorry. Isochoric. Okay? This is a situation where we have a fixed volume, right? We put it in an ice bath, and so my pressure decreases because my temperature goes down. Okay? If we had put it, guys, think about this. If we had put it in a boiling water bath, yes? If we had put it in a hot bath, what would have happened? Q, heat is gained to the gas, yes? That's the positive Q. Okay? If it's a fixed volume, then there is 0 work. The internal energy goes up. because essentially it'd just be a flipped graph like this. Everybody okay with that? People at home, how are we doing?
Good.
Thank you. Questions with that? Okay.
What exactly does isoporic mean again?
Isoporic means the volume doesn't change.
Oh.
Okay? Isoporic means the volume doesn't change. Now, the other thing that we can do, guys, is look at this. What does temperature equal? Temperature equals PV over NR. Okay? N is the number of moles, right? That should be a constant, essentially, for my system. Okay? Unless I'm adding more air in or more air out, that is a constant for my system. Okay? R is a constant value, right? So how can I tell that my temperature went down? Because if I took this P naught times V and this P final times V, yes? Guys, this is going to be greater. Yes? This is going to be greater. Look, temperature is dependent upon pressure times volume. Okay? Divided by this, right? But these are constants, so I don't really care. I'm just comparing the two. Okay? Which one is hotter? Well, which one has a greater P times V? Right? If it's the same number of moles, it's the same R. P times V is greater here. P times V is smaller here. Yes? So that tells me that I just went down in temperature. It tells me my internal energy goes down because internal energy measures the kinetic energy. It measures the temperature. Everybody cool with this? Okay. Questions? I'm not going to do the opposite of this. Obviously, the opposite, you might just write down. Opposite is a hot water bath, yes? Hot water bath basically flips everything around, okay? It would still look a graph like this, just our final and our initial is opposite. Okay, that's if we put something in a hot water bath. Cool? Okay. I apologize again, this is not the exciting type of physics class I like to teach. But welcome to college physics. Okay. Let's do another scenario where, we have pressure and volume, and this time we're going to fix volume, or we're going to fix the pressure, okay? So we have an object that can expand or contract freely, right? So our pressure is going to remain fixed, but we're going to allow this container to expand or contract. Like, think of it as a balloon, okay? Typically, the examples of this are a balloon. If you take a balloon and you put it in the freezer, what's going to happen to that balloon? Have you guys seen that?
Yeah.
The size decreases, yes? If we take a balloon and we put it in the oven, besides it melting, yes, what's the balloon going to do? It's going to expand, right? You maybe seen that where they take a balloon and put it like in a boiling water bath, and that's typically what we do, right? So let's, again, take this idea now, and instead of putting it in a hot bath, we'll put it in a cold bath. Let's put it in a hot bath, okay? So a hot bath. Again, the pressure is fixed, and here's what that means, right? In a balloon, the pressure, this can be confusing to people sometimes, right? In a balloon, the pressure on the inside and the pressure on the outside are equal, okay? In a balloon, the pressure on the inside and the pressure on the outside are equal. And that's because if there was a difference of pressure, right, the balloon would either be contracting or expanding, right? If they essentially think about pressure as forces pushing in and forces pushing out, yes? If there's a bigger force pushing in, the balloon's going to move in. If there's a bigger force pushing out, the balloon's going to expand. So what a balloon does is a balloon allows the pressure on the inside to equal the pressure on the outside. Most people would think that the pressure on the inside is bigger, right? But it's not bigger. We've just added more gas. We've added more air. So that's what's causing it to expand, right? But it maintains pretty much similar air pressure inside and outside. You guys okay with that? For the most part, okay? So let's think about this. Now, we put this object in a hot water bath, right? What's happening to my Q? Yeah, heat is gained by my gas. Yes? What's that going to do? That gives me a positive Q. Okay? It's going to be a positive Q. Now, what do you think is going to happen to the volume? Yeah, good. So in terms of the work then, right, if the volume increases, what's that going to do to my work? So let's do this. An increase in volume equals that's final minus initial, right? So that would have been final minus initial. Yes? Final 10 minus 5. Yes? So that is what? That's a positive delta V. Yes? We agree with that? If I have a decreasing volume, that's what? That's a negative delta V. Okay? So if I have an increasing volume, right? If I have an increasing volume, that's negative work. Yes, because it's negative times a positive. Okay? If it's decreasing volume, that's positive work. Okay? In terms of this, the volume expands. Okay? Volume expands, and so that gives me a negative work. Yes? Okay? And then what about this? What about delta U? Now, again, we don't have the specific numbers, so we can't really tell, right? But think about this. We have a positive Q here, and we have a negative work. So what happens to my internal energy? What happens to the temperature of the gas inside the balloon? You have two options here. Yes? What are my two options? I guess you could have three options. Yes? It could, like if this and this are equal, what's true about the temperature? Stays the same. Yes? If this is more than this, it heats up. If I have more energy added by heat than is expanded, right, then my gas inside heats up. Okay? If this is bigger than this, then it cools down. So this is really dependent. It's now equal, right? This is now equal the idea of, a positive Q plus a negative W. And so this means it could equal 0 or greater than 0 or less than 0. Yes? It all depends upon how these are related to one another. If one's bigger than the other. Okay? Let's go with that. Pressure, volume. What's that graph look like? Sorry, Brian. Jesse. Middle down low is not a good spot on the whiteboard. What's my pressure and volume graph look like? This situation. Well, what did we keep constant? We kept pressure constant, yes? So I should have some pressure P initial, yes? So I'm going to start here, right? Maybe that's my volume initial, yes? and then expands. So it's going to look like this. Volume final. Here's my graph. It's just something that's what we kept constant in this circumstance. So we allowed the, using the idea of PV equals nRT. As the temperature went up, we allowed the volume to go up. Okay? We allowed the volume to increase. And so we tried to keep pressure as constant as possible. Okay? I think constant pressure is, the hardest circumstance for us to imagine because I think conceptually it just doesn't make sense to us sometimes. But it is the ability of if I were to have, I just think of that balloon, right? And we're just allowing that balloon to continue to expand infinitely, right? We're not allowing the pressure to increase. We're just always allowing the volume to increase, which is going to not allow the pressure to go up, right? Like the fire syringe, we increase the pressure, and that's what causes the temperature to go up. Essentially, if we had our syringe just sitting here, and I put this in an ice bath, this piston would slowly go up and up and up and up, right? And so imagine I'm allowing that to go up, so I'm not allowing it to I'm not trying to withhold the gas in a certain area or a certain volume. Cool with that? Okay. Notice now, so this is isobaric. Okay. Isobaric is the idea that if you've ever looked at a bike pump or something that you use to add air to something, bars is a way that you measure pressure. So isobaric, isolate pressure. Pressure is constant, right? That's what that stands for. Okay. And notice now there is work that's done. Okay. That's the work that's done. Yes. In the isochoric, when we had a graph that looked like this, was there any work done? Because is there any area underneath my curve? No. So from the previous one, you might just write down no work done, right, on that graph because there is no area underneath the curve for the isochoric. You catching that?
Yeah, I didn't really get it because how could there be no work if our pressure stays the same?
No, I'm not talking about this one. I'm talking about the previous one we just did.
Oh, okay.
The previous one we just did, where we had a vertical line. There is no work done on. Now there's no work done on the gas or by the gas. Okay. When we do work, and we'll see that here in just a second. Yes, go with that. Okay. Questions with this, guys? What I could know, and actually this would be a good example with this, pressure times volume, which one is greater?
The one on the right.
The one on the right, yes? This is greater. So what that would tell me is that the temperature goes up. Because remember, temperature is dependent upon pressure times volume. So that would tell me the temperature goes up if I draw it like this, okay? Which would then tell me that my change in energy increases. And so then it would have to be this scenario. Yes? If the pressure times volume increases, my temperature goes up. My temperature goes up means I have more kinetic energy. More kinetic energy means I have a greater change in kinetic energy, which means, right, that this is greater than the work that was done. You guys okay with that? We see how it all kind of blends together. Okay, last one. This is what we're going to do in the lab. This is our lab example. Okay, so in the lab, here's what we do. We add weights on top, okay? What does that do? That applies some force down, yes? And it moves my piston a certain distance. So now we've just compressed our gas into this smaller area because our piston now is this long. You guys go with that? We've just compressed our gas like that. We have applied a force over some distance and we did work. Okay? Now, adding to over here, this is work done on the gas. On the gas. Okay? Work done on the gas decreases its volume. Right? Work done on the gas decreases its volume, right? Which is going to result, excuse me, in an increase in internal energy. Right? That's what we did here. That's what the fire syringe does. We do work on the gas really quickly. We don't allow the heat to dissipate, and we pump up that internal energy very quickly. Yes? That's what the fire syringe does. Okay? In the lab, we do it very slowly. All right? And when we do it very slowly, we allow Q to go away. We allow heat to dissipate out of our gas. You guys cool with that? Okay? Over here, work done by the gas is when our volume increases. Right? If our gas is pushing on the environment, right? If it is expanding back, yes, that is decreasing the internal energy. If the work, guys, think about this. When you do work physically, you lose calories inside of you, yes? Remember, work and energy are the same thing. Calories are a measurement of energy, okay? When I do work, I lose energy, yes? When I gain, when I eat, I gain energy, okay? So think about in terms of the gas. When the gas has work done on it, it gains energy, right? Because someone gave it energy through work. When the gas expands and it does work, and the gas does the work, it loses energy. Yes? Okay. So in our situation, what we are going to have is we're going to have Q is a negative. Yes? So Q, heat lost to environment. So that's a negative Q. Okay? In terms of W, work is done on the gas. That's a positive W. Yes? Okay? And what we're going to do, excuse me, is we're going to keep P times V constant. Right? That means temperature is constant. Okay? If we keep P times V constant, if we do this slow enough so that the energy gained by the work is lost by temperature or by heat leaving the system, yes, then our change in internal energy is zero. Okay? This is the circumstance where the heat lost equals the work that was done because we do it slowly. It's not insulated. It allows heat to go away, right? If we do this, we increase the temperature in here real quick, And then because there's no insulation, if this is a lower temperature on the outside, that temperature is going to try to go out, yes? Or that heat, temperature, that's not a great way to say it. The heat's going to go out, okay? And so the change in internal energy would be 0. Our graph then, pressure and volume, right, would look like what? We would have a big volume with a low pressure over here, volume initial, pressure initial, okay? And then we decrease the volume, we're also going to increase the pressure, okay? And we're going to take something that looks like this. So we're going to have a path that looks like this. Pressure final, volume final, okay? And so it's going to look like that. You guys cool with that? Now, PV and PV both equal T, right? They're the same thing, okay? And every position on here, PV is the same. The product of P times V is the same, okay? This situation is called an isothermal, okay? Isothermal. What do we keep constant in this case? Temperature is constant. Okay. Questions, guys? It's a lot, I know. It's a lot. And we sometimes don't know what questions we have until we actually try it, right? So I understand that.
This graph is about the system.
This graph is about this situation. Yep. This graph is this situation where we've done it slowly, right, to allow the temperature to remain constant, which allows whatever added energy I have from doing work to be lost to the environment, right, in this circumstance. Okay? It's the idea of taking this, right, as I push down, I'm increasing the pressure, decreasing the volume. I am doing work on the gas. When I do work on the gas, I give it more energy. But that energy is lost in the environment around it. Okay? Think about this. What if I pulled up really quickly? What if I expanded that volume really quickly? Yes? What would that allow? That would allow, that's work done by the gas. Yes? The gas is it's essentially now going the other way. Okay? Which means it's losing energy. It's losing energy by work, which would make the gas cooler, right? So, like, it's kind of cool. If I do this really fast, I can catch this on fire. If I do this really quickly, I, in theory, could make it ice. Yes? Like, I could make it so that it cools enough that it turns into ice. Yes? You get that? If I have it insulated, if I don't allow heat to come in, right? If I do it slowly, as I cool it down by expanding it, heat's going to come in because they want to be in thermal equilibrium, right? If it's 80 degrees out here, guess what? It wants to be 80 degrees in there, yes? Because there's that thermal equilibrium that it wants to be in, okay? So in theory, if I did this really quickly, I could turn it to ice just like going the other way. I could catch it on fire, which is pretty cool. You guys cool with that? So, and what we'll see, we're pretty much done, guys, but what we'll see is in a combustion engine, in a car's engine, it's just the repetition of this over and over and over and over, where we have a compression, we have an expansion, right? And this compression and expansion is your engine doing work. right? And what does your engine do work for? It does work to turn your wheels. And that's literally all the engine is used for. Okay, it's just to turn your wheels, right? And make your car go forward. And we cause it to, it's this repetition of up and down, up and down, up and down that we can connect to a shaft that can cause it to spin, right? And it's through this idea of compression and expansion, as well as, adding heat, losing heat by having a spark in there as well, okay? So what I'll do is I'll share that link that I think would be really helpful for you guys. And I'll leave, again, we've done thermal conductivity in terms of how heat transfers. So we might spend like tomorrow just doing problems with that. And then Thursday and Friday, just having you guys work through some simple questions dealing with this idea. And then next Monday, we'll kind of go through all of that, okay? I will post answers. I will post solutions, right? So you'll have both the answers as well as how I work through them, okay? But I might have you guys work through some of the conceptual questions as well, because I think some of those are really good, right? Because the numbers, guys, PV equals nRT. We can do that. The numbers are easy, right? It's just making sure we understand conceptually what's actually happening. So, cool? Okay. Thanks so much, guys. Have a great rest of the week. Make sure you're being respectful to the sub on Thursday and Friday. I will be checking my email, so if you have a major question, please check in. But I'm going to be super busy during the day with the kids. So, but I appreciate you guys' flexibility in all this. All right. Yes, this is recorded on YouTube as well. So I'll try to figure out how to upload it so you guys can see it. But yeah, it'll be on there too. Cool. Stick around if you have questions. Otherwise, we'll see you guys next Monday.
See ya.